Pulse width modulation, basically setting the duty cycle of a square wave. It has a whole bunch of uses like controlling the speed of a fan, using a digital mechanism on and off in order to provide an effective analog voltage, or just to create the square wave you need, whatever shape it happens to be. I've done a video on pulse width modulation. It's not the most comprehensive, but it'll do. If you think I should do a more in-depth, better one, feel free to leave a comment. But for now, the super ultra quick summary. You have a square wave. If you look at a rising or falling edge, let's say a rising edge. Rising edge to rising edge is a certain amount of time. This is your period or your wavelength, if you think of this as a sinusoidal. But this is your period. Then you have your high time and your low time. Let's say H is high, L is low, P is period. Your duty cycle is a percentage. It's high time over period times 100, and that's percent. If your high time and your low time are equal, let's say your period is 1 second, and high is half a second and low is half a second, then your duty cycle is 50%. It's high 50% of the time. If high was 3/4 of a second and low was 1/4 of a second, it'd be a 75% duty cycle. If high is 1/4 of a second and low is 3/4 of a second, it is a 25% duty cycle. If it's a solid low signal, that's a 0%. If it's a solid high signal, that's 100%. That's duty cycle. Pulse width modulation. Each square wave is a pulse in this case. All it's saying is changing the duty cycle. That's all it is. That's all it is. So like I said, last time when I did the astable square wave generator with the 555 timer, we did not get a 50% duty cycle. And I said that there were odd ways to kind of get it, but if you're willing to sacrifice 2 555 timers, you can just pick whatever duty cycle you want. Yes, it's twice the chips, but what you get is essentially perfect. You get exactly what you want every time. So if you're making a commercial product, you have to make decisions, but for something like me, someone like me, doing hobby work, hook 2 chips together, easy to configure, done. So here we go. We're going to use one timer, 555 timer, to create a square wave. All we care about is the period. We don't care about the pulse length. We just care about the period. And then I'm going to use a monostable to actually set the duty cycle. Now, how are we going to configure this? Think of the monostable, right? It's the timer. You press the timer and it goes for a certain duration. You press the button, it's on for a certain duration. Your square wave is just pressing the button for you. So your monostable has a duration that it's going to want to be on. And your astable, your square wave generator, all it's doing is pressing the button for you automatically. It's very simple. So we need 2 timers, and I wish I had a bigger board, but I'm going to do the best I can. So of course they each have their VCC pin. These get your positive power. They each have the ground pin. Those get your negative power. Your reset pin, once again, I'm just going to limit myself to 3 characters. You get the idea. The reset pin we're not using, so we'll hook that up to positive, just like before. And then the control with our capacitor to negative. This is going to be the square wave generator, the astable. So we're not using the control voltage on this one. I'm going to leave the control voltage on here alone for a moment. So for the astable, again, this is just the same. Watch the astable and monostable videos for an explanation. It's exactly the same setup. No changes. So for the astable, we have our 2 resistors and 1 capacitor voltage divider. So there's the voltage divider. We have our discharge pin connected up just like normal. And we have our threshold pin and our trigger pin shorted together, connected like normal. Same as in the astable video. The high of the duty cycle is set by both resistors plus the capacitor, and the low of the duty cycle is set by just this resistor and the capacitor. Then of course out. So it's just a square wave generator, and the square wave generator is pressing our trigger. Speaking of a trigger, here it is. The out, I'm going to connect to trigger. Remember, trigger for the monostable configuration, so this is the square wave generator, this is the timer, it's when it's low. Trigger starts the timer when its voltage goes low. So it'll be the low part, the part that's less than half, because remember the high time is greater than the low time in this standard configuration. So the low side of the square wave pulse is triggering the monostable. And again, the monostable is hooked up just the same as that video. We have the monostable RC network, just the 1 resistor, and we have the discharge and threshold pins connected together into that RC network, just like in the monostable video. And the timing here determines the length of the pulse, the duty cycle of the new square wave. We have out, which is our output. And I also have this odd resistor because of my BJT chips. I have BJT chips from Texas Instruments, from TI, and in order to get the full output voltage, I have to put this resistor here in parallel between output and the power supply. If you're using some other vendor's chips, you may not need it. And if you're using CMOS chips, you definitely don't need it because this is an issue only with BJTs. If you don't do this, you get the correct result, but it's not the full high voltage. You get 0 volts for low, but you lose some for BJT junction voltage drops on the high end, unless you add this resistor, and I still haven't figured out how it works. This is just magic. I'm continuing to work on it. If you know, let me know. But this resistor is magic. It just makes the voltage go high. I don't need it here because this is a BJT chip for me the same. And this is not going to put out the proper high voltage, but it doesn't matter because this is not the output I'll be using. I'm only triggering here. It doesn't matter if it's not the full voltage. So we don't need it there, or I don't need it there. And then we have our cont pin, of course. Now what do we do with that? Normally we just do this again because we don't need it. But here's the thing. Remember from the Monostable video how, in fact from the 555 timer video, how this works. Threshold is a voltage that turns the timer off when it goes high, above threshold. Trigger is a voltage when the voltage goes low, turns the timer on when it goes below trigger. So the voltage on trigger pin goes below trigger voltage, timer turns on. Voltage on threshold pin goes above threshold voltage, timer turns off. The RC network determines the charge time of the capacitor. That's always constant. Remember, it doesn't matter the voltages, it matters the percentage of charge. Capacitors always charge and discharge based on the percentage of charge they are versus the voltage applied. And I did a video on that too. So if we change the voltage that threshold is using, that trigger and threshold are using, to compare to the overall capacitor, like if it's completely discharged and you apply a voltage and you let it charge until it's effectively 100%, that's going to take the same amount of time no matter what, but it's not linear. Remember, it starts charging really fast and then it slows and slows and slows and slows. It's logarithmic. So by increasing or decreasing the voltage that triggers the timer to turn off, then it's going to take longer or shorter for the timer to turn off, which means we're extending or shrinking the pulse. If we turn down the threshold voltage, the rising voltage is going to reach it sooner, which means the timer is going to turn off sooner and our high time is going to be shorter. So we're going to have a lower duty cycle. And it's not going to change the period because this is setting the period. This is going to be sending pulses at a constant rate. This is how long the pulse stays high. This is how long between pulses. So here we're setting the duration of the high time, and here we're setting the period. And the low time is just a leftover. Whenever this stops being high, it's going to be low until it gets the new pulse. That's how this works. If we increase the control voltage, then it's going to take longer for the RC network to charge and raise the threshold voltage high enough to actually turn off the timer, so the pulse is going to be longer. So that's all it is. Control is another input. You just apply a voltage, and I'll just put that to say that's an input. This is how we set our PWM. You apply a voltage to control on the monostable to change the duty cycle, and then this sets the period. And there's your PWM. And if you have some sort of microcontroller that can output an analog voltage, or you have a DAC, some sort of digital to analog converter, or even a potentiometer. You can do it with a physical knob. You have a potentiometer acting as a voltage divider and apply a voltage. And you can just have a knob turning it up and down. Any way you apply a different voltage, you can control this. Now, if you use an Arduino, it just outputs PWM automatically. Of course, it only outputs 500 Hertz. It's always the same frequency, so maybe that's not good enough for you. So if you want a different frequency of PWM, you're going to have to do it yourself. But that's it. This one generates pulses, and this one uses the pulses as a repeating timer. There's one thing I haven't mentioned, though. Do you remember when I was doing the monostable video and I said that you have to release the trigger before the timer ends? If you're still holding the trigger, like if you trigger again, if you press the trigger 4 times, but the timer hadn't ended, nothing happens. It does not reset the timer. It does not extend the timer. You can trigger all you want within the timer. It's just going to be the same time. But if you're holding the trigger after the timer is trying to turn off. If this monostable is trying to go low and you're still holding trigger, you're not letting it. It's undefined behavior. Usually, it's just going to stay on until you let go, but that's not a 100% guarantee. But in any case, you're not going to get the result you want. The low time here, right? When this goes low, when output here goes low, trigger here turns the timer on. So if this tries to turn off, but this is still low, it hasn't gone back high yet, then you're still going to be getting the high end of your pulse. So you end up with a limit here. The size of the low pulse is the lowest duty cycle you can have, because the low pulse here becomes a high pulse here. If this is a 75% duty cycle, that means it's low 25% of the time, which means the lowest duty cycle you can have here is 25%, because you're going to have a 25% duration low signal becomes a 25% duration high signal. You can have longer, but you can't have shorter. Now, the internet had one solution, which was a high-pass filter. So just real quick, if you have, and I've done a video on this, if you have a square wave and you pass it through a high-pass filter, what you get is these crazy high spikes that come down like this and spike and spike and spike. That looks really useful because we're getting these nice short pulses. So the length of the low pulse is really small, which means the minimum duty cycle is really small, because that's what we want. We want this trigger pulse. When it goes low, we want it to trigger and then get out of the way. Just go low and then get out of the way. And the timer is going to do all the work. That's what we want, so we can have any duty cycle from 1 to 99%. The problem is, this is the way you hook it up. A high-pass filter is a series capacitor and a parallel resistor. So you take your output and you put it into the capacitor and you hook that across the resistor. Resistor goes to negative, resistor goes to trigger. This series capacitor removes the DC bias, right? So if you're using 0 volts low, 5 volts high, if you run it through a series capacitor, that 0 to 5 volt signal becomes a negative 2.5 to 2.5 volt signal. So almost all of the time, the signal is actually at 0. Almost all the time. Obviously, we've just failed. Now, there was another way to hook this up. Instead of hooking it to negative, we hook it to positive. So it's still a high-pass filter. Basically, we just biased it. The problem is we biased it with the full 5 volts in that case. So now we've got a 2.5 to 7.5 volt signal. Now it's not going low enough. So I fiddled around with this. I tried to make it work. It was just plain stupid. Bless the internet's little heart. But sometimes they are thinking too hard, and they had me thinking too hard for a while as well. Now, why did I deliberately tell you something that I knew was wrong? Learning. It's a good idea. When we want to take a square wave and get really short pulses, the first thing you think of is a high-pass filter. That's brilliant. That's like perfect. That's exactly what we want. But it's fiddly. And it's 2 more parts. You need another capacitor, you need another resistor, and you need more wires, more board space. So it's not the best solution. So forget that. Once I failed to get this working, I realized the internet was making me think too hard. These 2 resistors set the timing. The 2 resistors together set the high pulse length. This resistor alone sets the low pulse length. Together they set the period. All I have to do is pick a really small resistor here and then size this resistor to get the period I want. And that is going to result in an extremely low duration, low pulse, and all the rest of it is going to be high, just by changing the values of the resistors. Now, that's only if you're creating your own square wave. If you're not creating your own square wave, then you're going to have to maybe try the high-pass filter with a more sophisticated biasing setup. But I have to imagine it's an extremely rare situation where you're going to have to use somebody else's square wave to do something like this, where you have an existing square wave and you have to just adjust the duty cycle. I don't know when you do that. So we're just going to say, we'll just adjust this. So all you need is 2 555 timers. You need 1 capacitor for your control pin here. You need 2 capacitors and 3 resistors for the RC networks. I need an extra resistor to get the full voltage, but you can use a CMOS chip and you don't need that. And then you just hook up your control voltage to whatever you have. Potentiometer, voltage divider, microcontroller, whatever. Deviously simple, but nice and easy. And conceptually, you just have this timer pressing a button repeatedly for this timer. The robot uprising is coming swiftly. We're not even pressing our own buttons anymore. So let me show you on my oscilloscope, and I'll give you some values I'm using. So many wires. So I have my two BJT555 timers. They are the NE555P by Texas Instruments. I'm going to be using 5 volts for my power. So for timing the square wave, the A-stable, I'm using a 22 k ohm resistor and a 1 k ohm resistor. This gets me about 15, 16 milliseconds period. I'm aiming for roughly 60 hertz. It's close enough. So we get a nice, short, low pulse. And the capacitor is 1 microfarad. The timing for the monostable is about a 3.9 k ohm resistor and another 1 microfarad capacitor. The Texas Instruments datasheet recommended that the monostable RC network gives about a quarter of the A-stable RC network, so the period of the square wave should be about 4 times the duration of the timer at normal voltage. It's just a guideline. You might have to fiddle with it a bit. These values seem to work for me. Just have a bigger or smaller resistor by a little bit if it's not quite working. That mysterious VCC to output parallel resistor that I need for my chip is a 10K. The datasheet uses 1K, but I use a 10K. And I have a potentiometer set up. This is a trim pot, but it's a potentiometer set up as a voltage divider so that I can control the control voltage. So I can set the control voltage with this voltage divider. The size of the potentiometer doesn't matter except for how much waste current you have, how much waste power, because it's a voltage divider, so it's just percentage based. And that's the whole setup. So let's take a look. I'll set my power to 5 volts, and I'll give it a little bit of current, and it's currently running. Let me go ahead and turn this on. It's currently consuming about 6 milliamps, all told, with all the potentiometers and everything else in there. So it's not too wasteful. If you're using a CMOS chip with MOSFETs, then it's going to be much more efficient. And here's my lovely square wave. I've got it where this is 0, and each vertical division is 2 volts, so this is 2, 4.5, so about 5 volts. If I take out that parallel resistor, you can see that it drops down. Oh, wrong one. If I take out this wire, there we go. I need to use the correct wire. So just like before, you can see, look at the top voltage, and out and in and out and in and out and in. So all that resistor is doing is giving me back my full 5 volts. However, it does it. And then the rest of it is as normal. For my frequency, the separations are 5 milliseconds. So 5, 10, 15, and just a hair under. So I guess it's more like 14.5. So, you know, when I want as close as possible to 60 hertz, I'm going to want to change the resistor size a little bit. But right now, that's pretty good. And if I were to measure the output pin of the first timer, this right here, this is what I was showing you before was the output of the monostable, the final adjusted wave. This is the output of the A-stable. And it might be difficult to see, so let me zoom in. So you can see that I've got my low pulses very, very short. So if I make the low pulse big enough, then this is like 600 microseconds or something. That's pretty good. And as I bring it smaller and smaller, you can see, and it might be easier to see this way, you can see, I forgot my pointer. I've literally got my pointer in my other hand. I'm sorry. Here's my pointer. I will learn. So you can see the small pulses here, the low pulses, nice and quick, just what we wanted. And then all the rest of the time it's high. So if I bring it bigger, so this is the 5, 10, 15, that's how it works. So now let me switch my oscilloscope back to the proper output, and here's my adjusted wave. And I will now use a screwdriver to adjust my potentiometer. So this is setting my control voltage. I can turn the potentiometer up and down, and you can see that I am just changing the duty cycle all the way up, all the way down. So, and I'm going to turn it, if you watch, I've got it basically close to a 0% duty cycle. So I'm going to turn the potentiometer at a fixed linear rate. So I'm going to do it nice and slow and nice and evenly and keep talking as I do it. And you're going to see that as I go higher and higher and higher, suddenly, boom, it suddenly starts going faster. Do you see that? I'm going to turn it the other way at a steady rate. So it goes down very fast and then it slows way down. It's not linear because the charging of the capacitor is not linear. You set a voltage, voltage, and the timer turns off when the capacitor charges to that voltage. The capacitor charges more slowly. The higher the voltage is, the closer it is, the more charged. The more charged it is, the slower it continues charging. So if you have it set at a low voltage down here, then you can make very fine adjustments easily with this little screwdriver. But if you're way up here, then it's really difficult. I'm barely touching it. I am breathing on this potentiometer right now. And very small changes in voltage are very big changes in time because it takes so much time to get that smaller change in voltage. So that's just something to keep in mind, is you're going to want to adjust for the fact that it's logarithmic in your software. If you have software control for the percentage here, and volumes are like this too. If you've ever noticed when you're on your computer, if you have the volume down towards like 15% and you turn it down to 13%, then it's a big change. But if you're up at 85% and you put it at 87%, it's a much smaller change because they're just using a straight percentage factor on something that's logarithmic, and that's dumb. So it's the same thing here. If you want percentage duty cycle on a linear scale, you have to use an exponential function to counter the logarithmic voltage time relation. But that's all it is. Super simple circuit, and all I'm doing is changing the voltage on the control pin of the monostable, and I set my duty cycle. So that's how you set it if you want a controllable, live controllable PWM. But if you just want your nice 50% duty cycle, hopefully anybody watching the video hasn't gotten sick of waiting for me to get to that point, you just set it at 50%. You can pick any duty cycle, including 50, or whatever this roughly is. So whatever you want for your application, 2 timers, and you get your nice square wave. And that's all there is to it. And for safety, I will turn everything off. The best kinds of circuits are the circuits you can hook up in different situations with minimal changes and get different results. Or at least use for different applications, like picking a duty cycle and leaving it there, in which case you just figure out what ratio of resistors you need and put a permanent voltage divider in there. Or you can have a live controllable PWM signal, which works as a physical knob, microcontroller hooked up to DAC or whatever. And for me, this is part of my larger project of trying to turn DC into AC. My most popular, or I guess my second most popular video of all time, is filtering square waves to sine waves. So when I did that video, I came across a snag where I needed to amplify the signal because the low-pass filters were degrading the signal too heavily and I didn't have anything left at the end. And then that led me on a merry months-long chase into op-amps and everything else. So now that I have the knowledge I need, I can now create a filter stage with a post amp to turn DC into AC, and then I'm going to get into isolation transformers, and I'm going to show you how to take a single power supply and you can double the voltage, so a 5-volt supply becomes 10 volts, or a dual supply, using an amplifier that you have positive and negative voltages, so you can take a 5-volt power supply and turn it into a 5-volt and negative 5-volt power supply. It costs power, it costs energy, but you can do it with only one power plug. So look forward to these upcoming videos. While I go make them, I'll be seeing you.